Our universe could just stop. It could end without any warning. That's the idea behind vacuum decay. It's a real scientific theory. It says all of reality is balanced on a knife's edge. There's a fragile quantum architecture holding everything together, and there's a physics that could unravel it in an instant. The laws of nature might be temporary. They might not be permanent. A single bubble of new physics could form. It would expand at the speed of light, and it would mean something for everything. For atoms, for galaxies, the ground rules of existence might only be borrowed. You have to understand what nothing actually is. It's not just an empty void. The quantum vacuum, it's not empty at all. It's this seething, bubbling sea of activity, and that's because of Heisenberg's uncertainty principle. It allows for a temporary loan of energy from the universe. So in this quantum sea, particles and their opposites, matter and antimatter, they flicker into existence just for a moment, and then they annihilate and vanish. That's a verified prediction. It means empty space is the most energetic, dynamic thing we can imagine. It's the canvas for everything, and it's humming with potential energy. This quantum vacuum is the lowest energy state we've ever observed. It's the baseline, and permeating this whole restless sea are invisible fields. The most famous is the Higgs field. It's like an invisible syrup filling all of space. Particles move through it, they interact with it, and that interaction gives them mass. Without the Higgs field, electrons would zip around at light speed. Atoms could never form, we wouldn't exist. The values of these fields, their settings, they determine the laws of physics, the strength of gravity, the charge of an electron. The rules of chemistry, all of it depends on the stable configuration of these fields in the vacuum. But there's an unsettling question. What if our vacuum, with all its specific rules, isn't the only possible configuration? What if it's just one valley in a vast cosmic landscape? Scientists call that a false vacuum. It's stable for now, like a ball resting in a small dip on a mountainside. It feels solid, it feels permanent, but it's not at the absolute bottom. Somewhere out there, there might be a deeper valley, a true vacuum with a lower energy state. And if our universe is just resting in that higher dip, then its stability is an illusion, a temporary piece that could shatter in an instant. That shattering is vacuum decay. A transition that would rewrite every single constant of nature from the ground up. The Higgs field is like a sculptor, but it's not shaping stone, it's shaping mass. It's this field that's everywhere in every bit of space, and when the basic particles move through it, they interact. That interaction is mass. That's why an electron has its weight. A quark has its weight. Without this field, all those particles would be massless. They'd move at light speed. They'd never slow down. They couldn't bind. Protons, neutrons, they couldn't form. Atoms would be impossible. So stars, planets, life, none of that could emerge. The Higgs field gave the universe its substance. It provided the friction for things to come together. But then there's the measurement. When they found the Higgs boson, they measured the field's energy value. That number sets everything. It sets particle masses. It sets the strength of the forces. It's the signature on the blueprint, but the measurement suggests something. The value we see might not be the lowest possible state. It might be a local minimum. Think of a landscape, hills and valleys. Our universe isn't in the deepest valley. It's in a smaller dip, partway up a slope to us. It feels like the bottom. Everything seems stable, but the terrain goes further, and somewhere out there, a much deeper valley could exist. A true minimum. So the rules of our universe, the constants, they aren't necessarily permanent. They're written in a field that could, under the right conditions, find a lower state. Our physics, our chemistry, the nature of matter, all of it is contingent. It depends on the field holding its shape, and if that field were to shift, to collapse into that deeper valley, everything it sculpted would be unmade. Instantly, that marble in the dip, that's our universe. It feels stable. It's felt that way for 13.8 billion years. We've built everything from inside that dip. We look out at the stars from there, but the hill is still there, and the deeper valley is still below. In physics, that kind of stability has a name. Metastability, a state that's stable until it isn't. It's a temporary equilibrium, a pause. Our cosmic vacuum could be like that, a false vacuum. It's a local minimum of energy, not the global one. It's the shallow dip, not the bottom. For all of cosmic history, the marble hasn't rolled. The universe found a configuration that works. The fields are set. The constants are fixed. Life emerges, but the terrain of reality might have a steeper drop, a true vacuum with lower energy, and quantum mechanics tells us nothing is ever perfectly still. In that quantum foam, there's always a chance, a tiny probability. A bubble of that true vacuum could just form. A single quantum fluctuation, in just the right way, could be the nudge. It would be a tiny region where the Higgs field, maybe other fields, suddenly find that deeper valley. Their values would snap to a new, lower setting. The moment that bubble forms, the old rules inside it stop. The physics we know gets overwritten, and then it expands. The boundary of this new reality would rush outward at light speed. A wall of fundamental change rewriting the universe as it passes. There'd be no warning. From inside the old universe, we'd see nothing coming. One moment, the cosmos as we know it. The next, an advancing sphere of absolute transformation already here. The chance of this happening in any given year, in any cubic light year, is astronomically small. So small it likely won't happen for trillions on trillions of years. Maybe never, but the key word in metastability is maybe. The universe is on a knife's edge, not because it's likely to fall, but because the fall is possible. And the consequences aren't just destruction, they're redefinition. What waits in that deeper valley, we have no idea. The laws in a true vacuum are a complete mystery. They might not allow for atoms or forces or any structure we recognize. It might be a state so alien that existence itself changes. This isn't about an explosion. It's about an erasure, a quiet, instantaneous replacement of one set of cosmic rules with another. And the most haunting part is the timescale. This metastable state has held for eons. It could hold for eons more, or it could end before this sentence is finished. Our entire reality is built on a perhaps. The mechanism is called quantum tunneling. In our normal world, a ball in a valley can't just appear in the next valley. It would have to go up and over the hill between them. That's the classical rule. But for quantum particles, the rules are different. They can do something impossible. They can vanish on one side of a barrier and reappear on the other side. Like walking through a solid wall, it's not magic, it's probability. There's always a tiny chance, a non-zero chance, that a particle will just find itself on the other side. This happens constantly at a subatomic scale. It's the process that powers the sun. Particles in the sun's core tunnel through barriers to collide and fuse. That releases energy, so it's a real process woven into reality. Now take that idea and apply it to the cosmos. Our universe is like that marble in its shallow dip. The hill around it is an energy barrier holding our vacuum in its current state. Quantum tunneling says that given enough time, anything with a non-zero probability will eventually happen. Across the vastness of space, over eons, a random quantum fluctuation could provide a nudge. A tiny region of space could tunnel through that energy barrier. It wouldn't roll over the hill. It would just cease to be in the false vacuum and appear in the deeper valley of the true vacuum. In that instant, a bubble is born. Not an air bubble, a bubble of new physics. A perfect sphere where every fundamental field has snapped to a new, lower energy value. The laws inside are instantly changed. Irrevocably, the strength of forces, the nature of matter, the concept of particles, all of it is rewritten by rules we can't predict. This bubble is the seed of vacuum decay. And here the theory becomes truly alien. This bubble doesn't just sit there. The laws of physics demand it grows. The energy difference between the false vacuum outside and the true vacuum inside creates an immense pressure. The boundary of the bubble, the wall between the old universe and the new, begins to expand, and it doesn't expand slowly. It accelerates outward at nearly light speed. More terrifyingly, when this wall touches the surrounding false vacuum, it doesn't push it aside, it converts it. Mere contact with the bubble's boundary forces the Higgs field there to collapse into the lower state. It's like a spark touching gunpowder. The new physics propagates instantly, turning more of the old universe into the new. The bubble grows, and as it grows, its surface area increases. That lets it convert space even faster. From our perspective inside the old universe, there is no warning. One moment, the sky is normal. The next, an impossible wall of light, or something beyond light, is already on the horizon. It would be the last thing any observer ever saw, because the moment that wall touches you, the physics that allows for sight, for thought, for existence as we know it, ceases to be. The entire cosmos could be rewritten in a flash. A silent, instantaneous transition from one set of cosmic rules to another, triggered by a random quantum event so small we could never see it coming. The universe's ultimate fate could hinge on a ghost walking through a wall. This bubble would be the final frontier, a wall of transition, a line between what was and what would be. It expands not by force but by conversion. When the true vacuum forms, the energy difference between it and our false vacuum creates a pressure, an unstoppable pressure. The bubble wall, this membrane of energy, begins to move, and it accelerates instantly to the speed of light. It has to. This isn't an object pushing through space. It's space itself being rewritten, one Planck length at a time. Where the wall passes, the Higgs field drops into its lower state. The old constants vanish. New ones take their place. Every star, every planet, every atom in its path isn't destroyed in the conventional sense. It's unmade by a change in the instruction manual. The physics that allowed it to exist just switches off, and that's the true horror. Nothing can outrun it. No signal, no warning flash, no distress call can travel faster than light. The bubble's expansion is the ultimate speed limit of reality, turned against reality itself. From inside the doomed universe, you'd have zero warning. One moment, the night sky is filled with familiar stars. The next infinitesimal moment, a perfect sphere of transformation is already upon you. It would fill the entire sky in an instant. There's no approaching wall to see coming. By the time your eyes could register it, the laws of optics that allow sight would have already been erased. Your last conscious thought would be etched in a physics that was ceasing to exist. Life inside this new bubble, we can only speculate, and the speculation is bleak. The fundamental constants would be different. Maybe the strength of electromagnetism would be weaker. Atoms could not hold together. Electrons would drift away from nuclei. Every molecule in your body, in the air, in the ground, would quietly dissociate into a cloud of disconnected particles. Or maybe the new constants would be so extreme that matter as a concept is impossible. A universe of pure, featureless energy, or a cold, empty void lower than anything we can conceive. Stars could not burn, planets could not form. The complex structures from our specific, delicate balance of forces would be impossible. This isn't an apocalypse of fire and brimstone. It's an apocalypse of erasure, a silent, instantaneous correction to the cosmic ledger. Our universe is deleted not with a bang, but with a rewrite. The old code is replaced, and everything built upon it simply ceases to run. The wall touches Earth, and in that moment, the universe inside the bubble becomes a different place. The Higgs field, the thing that gives particles mass, it drops to a new, lower value. This isn't gradual, it's an immediate shift, a universal change in the ground rules. Every particle in our world would feel it at the same time. An electron's mass, a quark's charge, the strength holding a nucleus together. These aren't fixed. They come from their environment, and that environment has just been rewritten. Think about an atom. It's a delicate balance, a nucleus of protons and neutrons bound by the strong force. Electrons in stable orbits held by electromagnetism. Their masses, the strengths of those forces, they're tuned by the fields in space. If the Higgs field changes, that tuning is lost. The constants of nature become different constants. An electron might become thousands of times heavier. Its orbit would collapse, or it might become weightless, flying away at light speed. The strong force that glues protons together could weaken. Atomic nuclei would just fly apart, or it could strengthen so much that every particle crushes into a single, dense point. Matter as a stable thing would cease. Every molecule in the air, in the ground, in our bodies. It would undergo a silent, fundamental dissolution. Not an explosion, a quiet unmaking, the architecture of reality replaced with a new blueprint, one drawn for a much simpler, much emptier universe. This transformation sweeps outward. Our planet wouldn't be torn apart by forces. It would just stop being a planet. The structures from 13.8 billion years of evolution, stars fusing elements, galaxies spinning, they'd find their underlying physics revoked. A star relies on a balance, gravity pulling in, fusion pushing out. Change the strength of those forces even slightly, and that balance is obliterated. The star collapses into nothing or dissipates into a cloud. The galaxy itself would unravel, its gravitational glue altered. The cosmos would continue, but as a stranger. A place where the laws no longer permit complexity. A universe that is, for all intents and purposes, blank. This is an ending beyond the end of life. It's the end of the possibility of life, the end of chemistry, the end of light and structure. The stage itself is dismantled, leaving a new and empty theater, where different, unknowable rules now apply. That silent erasure is a prediction from physics. It came from a quiet shift in how we see reality. For a long time, a vacuum was just empty space. But then, in the 20th century, quantum field theory changed that. It showed that what we call empty isn't empty. It's a dynamic state, full of fields that fluctuate. And cosmology started asking big questions about where the universe came from and where it might end. These two fields came together, and from that, a new possibility emerged. The vacuum might not be eternal. In the 1970s, physicists started looking at this seriously. Sidney Coleman and Frank De Luccia were among them. Their work was key. In a paper from 1977, they laid out the math for what they called the fate of the false vacuum. This wasn't just philosophy. They built a rigorous model. They described, in the language of quantum field theory, how a bubble of true vacuum could form through a process called quantum tunneling. They calculated how its wall would expand at the speed of light, converting the universe as it went. That was the moment the idea moved from a what-if into a quantifiable branch of physics. It became a framework for asking a profound question. Is our universe stable, or is it just waiting to fall? For decades, it was a thought experiment. Then, in 2012, came a major piece of evidence. The Large Hadron Collider at CERN discovered the Higgs boson. This was more than finding a particle. It was a direct measurement of the Higgs field itself. Physicists could now put real numbers into those equations. They could analyze the shape of the field's potential energy landscape with new precision, and the results were unsettling. The data suggested the Higgs field's value might be in a metastable state. Our cosmic vacuum could be a false one, sitting in that shallow dip. The discovery didn't prove decay will happen. but it moved the idea from pure theory into a realm constrained by data. It became a legitimate scenario that our best models have to account for. This journey from speculation to theory to data-informed possibility shows something about science. It shows how theoretical physics deals with the biggest questions. It builds bridges from the smallest particles to the fate of the cosmos. Scientists aren't just cataloging what is, they're exploring what could be and what might yet become. They're mapping the fragile architecture of reality, trying to understand if the foundations we take for granted are built on stone or on a temporary ledge overlooking an abyss. The story of vacuum decay is that search, a search for answers written in the language of fields and probabilities, pointing toward a destiny we can only begin to see. That measurement, 125 gigaelectronvolts, it became this puzzle piece, finding the Higgs boson that was a celebration confirming decades of theory. But its precise weight, once you put it into the equations, told a more complex story. It was like finding a crucial part for a machine, and then realizing the part specifications suggest the machine might not be designed to run forever. The Higgs boson's mass reflects the Higgs field's energy value, its setting in the vacuum, and according to the standard model math, that specific number, combined with the top quark's mass, it paints a particular picture. It suggests the landscape of reality might not be a single, deep well. It might be that smaller dip on a hillside. Our universe's vacuum appears metastable. A false vacuum. Now, this isn't a certainty. The calculations are delicate. They depend on precise values of several fundamental constants, and the theoretical framework itself has margins of error. It's like trying to predict the stability of a vast, ancient structure by measuring the density of a single brick. You get a strong indication, but you can't be absolutely sure until you see the whole foundation. Some interpretations leave room for our vacuum to be truly stable, sitting in the deepest valley after all. Others suggest it could be even more precarious. But the central scenario from our best data is metastability. That shifted the entire conversation. Vacuum decay was no longer just a dramatic thought experiment from a physics journal. It became a quantifiable possibility, a potential destiny written into the numbers from the world's most powerful machine. The Large Hadron Collider didn't just discover a particle. It gave us a key, and that key opened a door to a profound question about the long-term future of everything. The equations had real numbers to work with, and those numbers whispered a warning. They told us the stage for our cosmic drama might not be permanent. It might be a temporary set, awaiting a silent, final curtain call from the laws of quantum probability. That cosmic infancy has another secret. Right after the Big Bang, the universe went through a violent growth spurt. It's called inflation. Space itself expanded faster than light. In a fraction of a second, a subatomic speck was stretched into something larger than our entire observable cosmos. Inflation did more than just make the universe big. It might be the event that locked our fate into place. It could be the reason we're sitting in this precarious false vacuum today. Think of the universe right after it was born. A seething, chaotic soup of energy, wildly fluctuating fields. Inflation acted like a cosmic iron. It stretched space so fast it smoothed out those wrinkles. It created the remarkably uniform universe we see, but in doing that, it might have also smoothed the Higgs field, pressing it into that specific, shallow dip. Across the entire expanse, inflation could have set the stage, placing every region of our cosmos into the same metastable state, a single, uniform configuration of physics. Primed with the same potential instability, some theories go further. They say the immense energy density that drove inflation might have acted as a temporary support. Like a scaffold holding up a building, the energy of the inflationary field could have propped up the Higgs field, keeping it artificially high, preventing it from finding a lower state. Then inflation ended, That energy transformed into the hot soup of particles of the Big Bang. The scaffold was removed. The Higgs field was left standing in its current position. Seemingly stable, but now on its own. It survived the transition, but was that survival guaranteed, or was it a narrow escape? The violent quantum fluctuations during inflation were tremendous. They're what seeded all the galaxies and cosmic structures we see, but those same tremors could have also jostled the Higgs field. In some regions, a fluctuation might have been just strong enough to nudge it over the energy barrier, triggering a bubble of true vacuum decay in the universe's first moments. If that happened, the outcome is both strange and reassuring. The bubble would have begun to expand at light speed, but inflation was expanding space itself much, much faster. Any decay bubble would have been inflated away. Stretched to such vast distances, it lies forever beyond our cosmic horizon. We could never see it, never be affected by it. Our observable universe, then, might simply be a region that got lucky. A patch where the quantum dice rolled in favor of the false vacuum, while other patches succumbed to decay and were eternally exiled from our view. This interplay is the key to a deeper question. Is our existence here a cosmic accident, a fortunate roll of the quantum dice during a turbulent infancy? Or was there something about the laws of physics that made this metastable state not just possible but necessary? For a universe like ours to form, understanding inflation's relationship with vacuum stability isn't just about the first moments. It's about whether our universe survived its birth by sheer chance, or by a deeper, more fundamental design. The silence of the cosmos, the fact that we are here to observe it, might be the result of a delicate balancing act performed in the first trillionth of a second of time. An act that set everything in motion and left us with a universe balanced on a knife's edge, waiting to see if its temporary peace will hold. That unsettling calculation isn't the end of the story. Our current physics, the Standard Model, it's a huge achievement, but it's incomplete. Those equations that point to metastability, they're built inside that framework. They could be missing entire chapters of reality. New physics waiting to be found might act as a cosmic safeguard. It could lock our vacuum into permanent stability. One of the most promising ideas is supersymmetry. It proposes a beautiful symmetry. For every known particle, quarks, electrons, photons, there should be a heavier superpartner. A selectron for the electron, a squark for the quark. These ghostly partners, we've never seen them directly, but if they exist, they change the math completely. Their influence on the quantum fields would reshape the energy landscape. That shallow dip we seem to be in, it could deepen dramatically, become the true and final valley. Supersymmetry could turn our false vacuum into a true one. It could be the missing piece, the guarantee for the universe's long-term survival. Other grand theories point the same way. The quest for a theory of everything to unify all forces might reveal hidden structures. Some models talk about extra dimensions of space. They suggest our three-dimensional reality is a membrane floating in a higher dimensional cosmos. The stability of our vacuum could be anchored by that connection. A cosmic mooring line we can't yet perceive. Even dark energy, the mysterious force accelerating the universe's expansion, it could play a role. That constant pressure might be subtly reinforcing the vacuum, preventing it from tunneling into a lower state. This search for safeguards, it isn't just philosophical. It's the driving force behind the next generation of discovery. Future particle colliders, more powerful than any before, are being designed with this in mind. They'll probe energies never seen, hunting for the fingerprints of supersymmetry or other new phenomena. Astronomers peer into the deepest cosmos, not just to map galaxies, to look for any sign of exotic physics in the behavior of the early universe. They're searching for evidence that the laws are not just temporary, that they're eternally anchored. Until we find that evidence, vacuum decay stays on the books, a haunting possibility. It's less a prediction and more a profound question mark. a reminder of how much we still have to learn. Our universe has lasted for billions of years. It may last for trillions more, but its ultimate fate rests on discoveries we haven't made yet, on physics we haven't written. The silence of the cosmos for now holds a question, and it holds a hope. The numbers are hard to grasp. If our vacuum is metastable, its half-life is staggeringly long. Some estimates put it at 10 to the 100th power years. That's a 1 with 100 zeros after it. The universe is about 10 to the 10th years old. 13.8 billion. So this half-life is a number so vast it dwarfs any human timescale. The chance of a decay bubble forming in our cosmic neighborhood in any given year is vanishingly small. For all practical purposes, on the stage of human history, it's zero. You're more likely to win every lottery on every planet in the galaxy for 1,000,000 years straight. The event is so rare it borders on the impossible, but in the grand theater of eternity, the word impossible loses its meaning. That's the probability paradox. An event can be so unlikely it will almost certainly never happen to you, or to your civilization, or to your galaxy. But if time and space are truly infinite, or if our universe is just one bubble in an eternally inflating multiverse, then the math shifts. Given an infinite canvas and infinite time, anything with a non-zero probability, no matter how tiny, must happen, not just once but an infinite number of times. From that eternal perspective, vacuum decay isn't just a remote possibility. It becomes a statistical certainty. Somewhere, at some point, a bubble will form. The question then isn't if, but when and where. Our existence here and now might just mean we are in a region where it hasn't happened yet. We're living in the calm before a storm that may never reach us or may arrive in the next instant. This paradox forces us to confront scales of reality our minds aren't built to handle. We think in centuries, in millennia, but cosmology deals in eons that make millennia look like the blink of an eye. On those scales, even the most solid mountain is a temporary ripple. The most stable star is a fleeting spark. So what does it mean for something to be stable? Our entire cosmic epoch, with its galaxies and life, could be a brief, bright interlude in an endless saga of transition and change. The silence we perceive as permanent peace might just be the deep breath before a transformation that is, in the fullness of eternity, inevitable. This isn't a reason for alarm. It's a reason for a profound shift in perspective. It asks us to see our universe not as a finished product, but as a moment in a process. A temporary configuration of laws, beautiful and complex, holding its shape against the relentless ticking of quantum probability. Our universe might be one bubble in a cosmic foam. That's the picture from eternal inflation. It stretches reality far beyond what we can see. The Big Bang wasn't the beginning of everything. It was a local event. A phase transition inside something much larger, something eternally inflating. In that inflating sea, the quantum foam sometimes settles. A region stops inflating violently. It relaxes into a stable state, or a metastable one. That region becomes a bubble universe with its own random laws, its own constants, its own version of reality. An infinite number of these bubbles could be constantly forming, like bubbles in a vast, boiling pot. Each one is a separate cosmos, isolated forever from the others by walls of still inflating space, expanding faster than light. Our entire observable universe, all its galaxies and history, might be inside a single one of these bubbles, and if that's true, then vacuum decay isn't an ending. It's a transition. It could be the process where our bubble gets invaded. A new bubble of a different vacuum state with different physics could form inside our universe. Or from the outside, the wall of a neighboring bubble universe, expanding through the inflating background, could finally collide with ours. In either case, the boundary where the two sets of physics meet would be a wall of conversion. A rewriting front. Our local laws would be replaced by the laws of the invading bubble. That transforms the idea. It's not a solitary catastrophe anymore. It's part of a vast dynamic ecology. The end of our universe in this multiversal view isn't the end of existence. It's a local event in an infinite landscape. One bubble pops or merges with another while countless new ones are born. This perspective is humbling and strangely reassuring. It means the fragility we perceive, the knife's edge our physics seems to balance on, might be common. A phase that many, maybe most, bubble universes go through. Some bubbles might form in a true, stable vacuum from the start. They're the cosmic fortresses, destined to last forever. Others, like ours perhaps, form in a metastable state. They're the temporary structures in the multiversal landscape, beautiful, complex, but destined to eventually be overwritten. For us, inside this bubble, the threat is no less absolute. If a new vacuum bubble forms here, or if one collides with us from outside, the outcome is the same as the classic vacuum decay. A wall of new physics expands at light speed, erasing our universe as it passes. Our story ends, but the grand narrative of the multiverse continues. New bubbles with new possibilities nucleate in the eternal dark. This framing invites a shift in how we see our place in reality. We're not just inhabitants of a universe. We might be temporary residents of one particular configuration of physics, in one bubble among an infinity. Our quest to understand the stability of our vacuum, then, is also a quest to understand what kind of bubble we live in. Are we in a fortress or a temporary shelter? The answer lies in the physics we have yet to discover, written in the silent fields that fill our tiny, beautiful, and possibly fleeting corner of everything. Looking for evidence is like hunting for ghosts. You can't watch the event itself. A decay bubble would move at light speed, and its arrival would be its own announcement. There's no signal that could outrun it, no warning system we could build, so scientists look for echoes, for subtle scars left on reality that might tell a story. A story of instability or of past collisions in a much larger multiverse. Their main telescope is the cosmic microwave background. That's the oldest light in the universe. A fossil glow from when atoms first formed. It's a snapshot of the infant cosmos, and it's remarkably smooth. But if our universe had a violent encounter early on, if the wall of another bubble universe collided with ours during inflation, it would have left a distinct imprint. A kind of circular bruise, a strange temperature pattern on this ancient sky. Researchers have scanned the data with immense care, looking for these signatures. So far, they've found none. That silence is itself a clue. It places limits on what kinds of multiverse models could be true. It tells us that if our bubble was born alongside others, any collision must have happened far beyond our observable horizon. Or not at all. The cosmic background radiation, in its profound uniformity, suggests a childhood of isolated calm for our pocket of reality. The other great tool isn't a telescope. It's a microscope of unimaginable power. Particle colliders like the Large Hadron Collider aren't just discovering particles, they're mapping the shape of nothingness itself. By measuring the properties of the Higgs boson and the top quark with greater precision, physicists are taking the temperature of the quantum vacuum. They're refining the numbers that go into the equations that describe the Higgs field's potential energy landscape. Is it a deep U-shaped valley? Or is it that shallow dip on a hillside? Each new decimal point in their measurements sharpens the picture. Future colliders, probing at even higher energies, could reveal new particles or forces. Forces that completely reshape this landscape. They could find the superpartners predicted by supersymmetry, which would likely stabilize the vacuum. Or they could find nothing new, leaving the metastability scenario as our best description. This experimental work is slow. It's meticulous. It's far from the drama of an instant cosmic erasure. But this is how we build knowledge. It's how we test whether the foundations of our reality are permanent or provisional. We may never get a warning that vacuum decay has begun. But through this patient, indirect detective work, we might one day answer a more profound question. We might determine if our cosmic home is built on the bedrock of a true vacuum, destined to last as long as time itself, or if we're just temporary tenants in a beautiful, metastable configuration, enjoying a borrowed stability on the slope of a deeper, unknown valley. The quest isn't for a forecast, it's for understanding, an attempt to read the architectural plans of existence, to see if the word forever is written into its blueprints. Or if it was only ever penciled in. This fragility hits something deep. We've always looked to the cosmos for permanence, the mountains, the oceans, the stars. They were a stage, something far more enduring than our lives, and vacuum decay takes that comfort away. It says the stage itself is temporary, that the constants, the rules of existence, they're not eternal truths. They're a contingent arrangement, and it could be fleeting. That's a different kind of threat, the ultimate existential risk, not a risk to life or to Earth. A risk to the operational logic of reality itself. No technology could shield against that. No civilization could advance enough. You can't build a wall against a change in the concept of wall. It shifts everything, the ground beneath questions of meaning, of legacy. If the cosmos can end in an instant, erased not with a climax but with a silent, random quantum event, then what is purpose? Some philosophies find a resonance here. It echoes old ideas, the impermanence of all compounded things. This possibility, it doesn't make things meaningless. It can reframe where meaning is found. If our stable epoch isn't guaranteed, then the experience within it becomes more precious. The art, the discovery, the connection. Watching a sunrise, it's valuable not in spite of its finitude but because of it. Our projects, our memories, our efforts to understand, they all happen within a temporary window. A window of cosmic grace. It could stay open for eons, or it could close before you finish this thought. This isn't despair, it's a clarified perspective. It asks us to consider value in a new light. If the universe offers no promise of permanence, then meaning isn't something we uncover, written into eternity. It's something we create, something we affirm within the time we have, however long that is, the search for knowledge, building community, expressions of beauty. They aren't diminished by a transient cosmos. They become brave assertions, beautiful assertions against the silent dark. They are the universe in our corner of it, becoming aware of itself. Reaching for understanding, even as it contemplates its own possible instability. That reckoning is maybe the most human response. It moves us from a passive fear of an end to an active reflection on what we do with the gift, the astonishing, fragile gift of a universe that allows for such contemplation at all. This abstract terror has found its way into our stories. Vacuum decay, that silent and absolute finality, has moved from physics journals into science fiction. It's a modern kind of apocalypse, not from gods or monsters, but from mathematics. Writers and filmmakers use that terrifying elegance. The end isn't just possible, it's a scientific certainty, and that changes the story. The drama isn't about stopping the end. It's about what you do in the face of it, how you live when the universe has an expiration date. In Liu Cixin's The Three-Body Problem, there's a central revelation. An advanced civilization tells humanity a fundamental truth about the cosmos, that the universe's natural state is a deadly, lower-dimensional void. Our stable, three-dimensional reality is a fragile bubble. A temporary sanctuary, and it is decaying. It's not vacuum decay in the strict physics sense, but the parallel is powerful. The end is presented as a cosmological fact. A law of nature, there's no appeal, so the human drama isn't about finding a weapon. It's about grappling with meaning, civilization, legacy, love, across an abyss of doomed time. The science becomes a stage for the most profound human questions. Television has explored this too. In an episode of Doctor Who, the Doctor confronts a being called the Beast. It claims to be from before the universe. It speaks of a time before time when the universe was smaller, denser, with different physical laws. The idea that a previous alien set of cosmic rules was overwritten by our own Big Bang, that's a narrative cousin to vacuum decay. It flips the script. It suggests our beginning might have been another reality's end. These stories use the scientific concept as a springboard. They blend hard speculation with raw existential themes. They ask how identity and morality persist when the very framework for existence is provisional. This cultural journey is significant. It shows how the most esoteric frontiers of theoretical physics can permeate our popular consciousness. Complex equations about field potentials and quantum tunneling get distilled into potent narrative symbols. They become metaphors for our own fragility. For the temporary nature of all we build, these stories aren't trying to teach the math, they're trying to translate the feeling, that chilling awe from understanding that reality might be balanced on a knife's edge. By embedding this science in human drama, they let us confront the idea safely, from a distance, to explore the emotional landscape of an ultimate end. And to find within it not just fear but reflections on courage, connection, the strange beauty of a temporary cosmos. The physics provides the mechanism. The stories provide the meaning, and together they remind us that our search to understand the universe is also, always, a search to understand ourselves within it. The common picture is fire and ice, the universe collapsing or fading into cold darkness. Vacuum decay is different, it's stranger, quieter. This isn't about running out of energy. It's about the rulebook being replaced. To start, it's not an explosion, no wall of fire, no blast wave. Matter isn't torn apart, the change is a rewrite. A phase transition, like water freezing. At a certain temperature, the molecules rearrange. It's still water, but now it's ice. A flowing liquid becomes a solid. Vacuum decay would be like that, but for reality itself. The fields in space would snap into a new configuration. The temperature is the energy state of the quantum vacuum. The freezing is the instant it drops lower. The universe isn't destroyed by a force. It just stops being the universe we know. It becomes something else. Second, this isn't a proven fate. It's a serious hypothesis. A logical consequence when you take our best measurements and plug them into our best model, the standard model. But that model is incomplete. It's a magnificent map, but it doesn't show the whole territory. There could be new physics, undiscovered particles or forces that change the calculation completely. They could show our vacuum is actually in the deepest valley, perfectly stable. So as scientists, we take the possibility seriously, but we also hold it lightly. It's a fascinating implication of our current knowledge, not a prophecy. Finally, the event itself would be silent, instantaneous from any inside perspective. No sound in space, of course, but more than that, no traditional sensory event to perceive. The laws governing light, sound, even your neurons, would change the moment the bubble's wall reached you. Your perception would be the last instant of your old physics. No time to feel fear, no dramatic spectacle. One set of rules would simply stop, and another would begin. Clarifying this moves the discussion away from cosmic bombs, doomsday explosions. It grounds us in the actual, nuanced science. A science pointing to a possibility more subtle than destruction. More profound, not an end with a bang, a transition with a whisper, a reminder that reality in its deepest layers might be more malleable, more mysterious than our everyday experience lets on. Our universe is winding down, that's the second law. Entropy always increases, disorder always grows over eons. That leads to the heat death. Everything just spreads out. A lukewarm sea, stars go dark, black holes evaporate, all motion stops. It's a slow fade into maximum entropy, a final quiet, but vacuum decay is a different exit. A shortcut, it wouldn't just speed things up, it would erase the board, start a new game. The instant a bubble of true vacuum forms, the physics that defines entropy gets rewritten. The arrow of time, that flow from order to disorder, it's not an absolute. It comes from our specific laws. It emerges from how our quantum fields are set. If those fields change, time's direction changes. The new vacuum would have its own entropy floor, its own starting point for disorder, and that floor would be far lower than anything here. Think of our universe as a sandcastle. The heat death is the tide coming in, slowly washing it away until the sand is flat. Vacuum decay is different. It's like the beach turning to solid glass. The castle, the sand, the very idea of grains, all of it is replaced instantly by a new, simpler substance. That immense complexity is gone, not because it was scattered, because the ingredients for complexity ceased to exist. That challenges how we think about an ending. Our stories are about decay, about running down, but this is a transformation, a sudden shift into a different physical reality. The heat death is the ultimate dispersal. Vacuum decay is the ultimate replacement. One leaves a blank, cold canvas. The other replaces the canvas with a different material, one that may not allow painting at all. In that new state, the things we know, galaxies, planets, living cells, they wouldn't just be unlikely, they'd be impossible. The laws wouldn't permit them. So the end isn't a scattering into chaos, it's a leap into a new, simpler order. A state so stable, so minimal, that our universe looks like a temporary dream. A feverish dream of complexity that reframes the whole story. Our journey from the Big Bang to the far future might not be a long slide into darkness. It could be a bright, complex interlude, suspended between two kinds of simplicity. The silence of a true vacuum might be the universe's final answer. Its most stable one. There is no warning system we could ever build, no shield, no plan to evacuate. That's the core of the impossibility with vacuum decay. It starts with the speed. The bubble wall expands at the speed of light. That's the universe's ultimate speed limit. No signal can travel faster. So the moment a bubble forms, even on the far side of the galaxy, its edge is already moving toward us at that maximum speed. A detector placed light years away, meant to send an alert, would be destroyed the instant it saw the wall coming. The alert signal and the wall itself would race toward Earth at the same speed. They would arrive together. The first warning would be the event itself. Our entire history would end in the same instant we learned it was ending. You can't outrun a rewrite of physics. Prevention is an even deeper impossibility. To stop vacuum decay, you wouldn't be fighting a force. You'd have to stop the quantum field itself from tunneling. You'd need to lock the Higgs field into its current value, not in a lab, not on a planet, but across the entire cosmos. Every cubic centimeter of space, from here to the edge of the observable universe and beyond, would need to be stabilized at once. The energy required is beyond any scale we can comprehend. It would exceed the total mass energy of the universe many times over, and more fundamentally, it breaks causality. You can't affect a region of space faster than light can get there. By the time your stabilizing effect reached a distant star, the decay bubble, also moving at light speed, could have already formed there and begun its journey back. You'd be in a race you could never win, against a process rooted in a random quantum dice roll. This paints a stark picture of a fundamental limit. Throughout history, intelligence and technology have been tools for solving problems. For pushing back against threats, we build shelters from storms, medicines for illness, spacecraft to leave the planet. Our story is one of expanding control over our environment. But vacuum decay represents a wall, a category of problem that exists outside the domain of solutions. It's not a challenge to be overcome with better engineering or more powerful computers. It's a condition of the stage itself. If the stage is temporary, the play must end, no matter how clever the actors have become. That absolute helplessness is perhaps the most unsettling part. It marks a boundary for any civilization, no matter how advanced, a reminder that we exist within a system of laws, not above them, and those laws might contain the seeds of their own expiration. Yet this realization isn't a call for despair. Instead, it reframes the value of everything we do inside this temporary window. Our science, our art, our connections, they gain their meaning not from lasting forever, but from the fact that they exist at all within a cosmos that permits such richness. The impossibility of preventing this particular end highlights the extraordinary, fragile miracle of the present. A stable universe is not a given, it's a gift. And our response to that gift, in the face of ultimate limits, is to keep exploring, creating, and seeking to understand, even if some answers tell us there are walls we cannot scale. The search itself becomes the most profound affirmation of our temporary, precious place in the story. This knowledge is in a strange place. It's a risk, but not one we can face directly. So what do we do with that? If our universe is metastable, just hanging in a temporary balance, does that fact come with any kind of responsibility? That answer isn't in the physics. It's in how we respond to what the physics shows us. Some people think this actually sharpens our focus on other risks, the ones we can actually do something about. Like advanced artificial intelligence or biotechnology, if the whole cosmic stage is fragile, then it gets even more important to protect the play from the dangers we can control. It becomes an argument for wisdom, for being careful stewards of our own growing power, to make sure that if the universe gives us a long window, we don't shut it early ourselves. Another view looks inward toward meaning. The chance of an instant, silent end could be seen as a call to value the present, not with frantic hedonism, but with a deeper appreciation for what defines a life. The connections we make, the beauty we create and see, the pursuit of understanding itself. If no long-term future is guaranteed, then the quality of our moment becomes everything. This doesn't mean we stop planning for tomorrow, but it can ground those plans in the value of today. It asks what matters most inside this temporary grace of a stable cosmos. This ethical side is abstract because the risk isn't actionable. We can't build a stabilizer, we can't vote on quantum probabilities, but the intersection is still powerful. It shows how our deepest scientific understandings spill over into philosophy. They force us to confront how to live. Do we let the shadow of a distant end darken our days? Or do we let it clarify the light we have? Maybe the most human response is to hold both, to work responsibly toward a future for our civilization, and to also cherish the astonishing fact that we're here at all. In a universe that can even contemplate this, the theory of vacuum decay in its silent uncertainty doesn't give answers, it just holds up a mirror. Asking what we see reflected in a cosmos that might be, in the deepest sense, on borrowed time. An asteroid can reshape a continent, a gamma-ray burst can sterilize a planet. These are cosmic catastrophes, but they're local. They leave a universe intact around them. You could have survivors in a bunker deep underground or on a world sheltered somewhere else. The framework for existence stays. Even the sun's death 5 billion years from now is just one star's finale in a galaxy of hundreds of billions. These threats operate within the system. They're disasters written in the language of our known physics. Vacuum decay speaks a different language. It doesn't destroy things within the universe. It replaces the universe itself. There's no bunker deep enough, no planet far enough. The moment its boundary passes, the concept of shelter loses all meaning. The laws that allow for rock, for metal, for protected caverns, they just cease to apply. It's not a threat you can hide from. It's a change in the rules of hiding. Then there's time. The heat death of the universe is the ultimate slow fade, a process stretched over timescales so vast they numb the mind, trillions upon trillions of years of gradual dimming. An ending so distant it feels almost like a philosophical abstraction. Vacuum decay carries no such patience. Its probability in any given year is infinitesimally small. But unlike the heat death, it's not tied to a slow, inevitable thermodynamic clock. It's governed by quantum chance. It could happen 10 trillion years from now. Or it could have begun before you started listening to this. The timing isn't scheduled, it's random. This combination, total in space and random in time, places it in a category all its own. A singular kind of peril, so you can map a spectrum. On one end, threats to a species or a biosphere, asteroids, supervolcanoes. Further along, threats to a planet's viability, like a star going nova. Then, threats to all life in a galaxy, maybe from gamma-ray bursts. Beyond that, the slow, universal winding down of heat death. And then, in a separate box entirely, sits vacuum decay. It's not a threat to life or to planets or to galaxies. It's a threat to physics, a danger not to the actors or the set, but to the stage itself. If the other risks are about losing the game, this one is about the board dissolving mid-play. Understanding that distinction is crucial. It reframes our place. We often worry about our survival, but vacuum decay asks a more fundamental question. It asks about the survival of the arena in which survival is even possible, and in doing so, it highlights the gift of a stable reality, an astonishing, non-negotiable gift. One we've received without knowing for how long we get to keep it. The quantum world has this mystery, the measurement problem. It comes down to a simple, baffling fact. Particles like electrons, they exist in a haze of possibilities, a superposition until you measure them, then they settle, a definite position, a definite property. The math is clear, but what it means isn't. What counts as a measurement? Where's the line between the fuzzy quantum realm and the definite world we see? Some interpretations, like Copenhagen, bring in the observer. The idea is that observation itself causes the wave of possibilities to collapse into a single reality. That's led to a speculative idea, a controversial one, that consciousness, the subjective experience of an observer, might shape physical reality. It's a bridge between mind and cosmos. Many physicists find it troubling, unscientific, but it persists. Now place that idea next to vacuum decay. In this view, our universe exists in a superposition. It's both stable and decayed, both false vacuum and true vacuum, simultaneously. Until what? Until it's observed. If consciousness collapses quantum states, then our act of looking at the universe, measuring the Higgs boson, contemplating fate, that becomes an act of participation. We're not just reading the story, we're helping to write it by the fact of our attention. That leads to a dizzying question. Could the presence of observers like us, by continuously measuring reality, be what keeps the wave function from collapsing into decay? Are we holding the universe in its current configuration? Through an endless collective act of observation, mainstream physics rejects this overwhelmingly. The prevailing view is decoherence, interaction with the environment. That's what makes quantum systems behave classically, not consciousness. A measurement can be made by a rock, a camera, a detector with no mind. To say human awareness stabilizes the cosmos misreads scale and mechanism. It places a burden on a phenomenon that emerged recently, on a tiny planet, in a universe stable for billions of years before we arrived. But even as a thought experiment, it forces a reflection. In a cosmos that could be annihilated by a random, mindless event, what's the significance of our consciousness? If we're just passive witnesses, then our awe, our science, our art, they're fleeting. Beautiful but irrelevant to the cold machinery. But if our observation is part of the machinery, however small, then our existence gets woven into cosmic stability. Our quest for understanding becomes not just exploration, but a subtle act of maintenance. We're not just inhabitants, we're custodians, using the light of awareness to illuminate and maybe to anchor the temporary stage we stand on. This might be more poetry than physics, but it speaks to a need to find meaning, maybe a quiet responsibility, in our strange position as the universe's way of knowing itself. That bridge from possibility to annihilation, it's described by a kind of mathematics, a startling elegance. At the center of the theory, there's the Coleman-De Luccia Instanton. It's not a particle, it's not a force, it's a mathematical shape, a solution to the equations of quantum field theory, and it describes that impossible journey. How a universe tunnels from one state to another, the Instanton is the answer. It represents the most probable path, the path for the quantum fields to make that leap. To visualize it, physicists use a subtle trick. They rotate time. They rotate it into an imaginary dimension that transforms the familiar flow of time. It becomes a kind of spatial direction. In this Euclidean space-time, the Instanton appears. It's a perfect symmetrical bubble, a four-dimensional sphere. Its surface is the mathematical description. It describes the tunneling event itself, the moment the false vacuum ceases to be and the true vacuum begins. The action of this Instanton is a crucial number. It calculates the probability for the decay to occur in a given volume of space over a given time. The math is precise. It accounts for the energy difference, the difference between the two vacuum states. It accounts for the thickness of the barrier between them. It even accounts for the influence of gravity. Gravity can actually suppress the decay rate, the curvature of space-time around a massive object. It makes it harder for the bubble to nucleate. In regions of extreme density, like near a black hole, the universe might cling. It might cling a little more stubbornly to its current state. This interplay is woven in. It's woven into the geometry of the equations. They tie it together. The quantum world of fields and the cosmic scale of gravity. They tie it into a single, coherent picture. There's a stark beauty in this, the most absolute existential threat we can conceive. It's not described with chaos. It's not described with noise. It's captured by clean, symmetrical differential equations. The potential end of all structure. It's reduced to a problem in calculus. This is the strange power of theoretical physics. It can take a concept that chills the soul, and translate it into a language of symbols and operations, a language where questions about forever become questions about the shape of an abstract landscape. The equations don't care about meaning. They only describe mechanism with a cold, breathtaking grace. They show us that if our universe is to end, it will do so. Not randomly, but according to a specific, calculable logic. A logic written in the silent language of mathematics, waiting in the fabric of space itself. That landscape of mathematics, it's still being mapped, and the question of whether our universe is stable, that's one of the big projects of our time. It's happening on three different fronts, three ways of listening for an answer. First, there's the hunt for precision. On the smallest scales, our uncertainty right now, it comes down to delicate measurements. The Higgs boson, the top quark. Future particle colliders are being designed to sharpen those numbers to a razor's edge. There's a proposal for a future circular collider. A ring over 50 miles around. Its purpose would be to produce Higgs bosons, millions of them. With that many, physicists could measure their properties. With a precision we can't reach today, they'd probe the subtlest interactions, how the Higgs field couples to other particles. It's not just about finding new particles. It's about taking the temperature of the vacuum with a thermometer 1,000 times more sensitive. Every decimal point they gain, it refines the shape of the energy landscape in the equations. It could show the dip we're in is a deep, secure well, or it could confirm with much greater confidence that we're on a metastable slope. That collider is a microscope. Aimed at the foundation of reality, the second front looks outward to the largest scales. Cosmologists are astronomers of the ancient past. They use telescopes as time machines. Their target is the cosmic microwave background, that fossilized light from the universe's infancy. New observatories will map its subtle variations. With greater resolution, they're searching for imprints of the universe's most violent early moments. A collision with another bubble universe in that primordial foam, it would have left a distinct signature. A circular signature, a kind of cosmic bruise on that ancient sky. Not finding that signature is also data, powerful data. It tells us that if our bubble is part of a multiverse, any collisions happened far beyond our horizon. Leaving our local pocket untouched, these surveys also look for other anomalies in the large-scale structure of the cosmos, anything that might hint at a different set of physics. In the distant past, or even in other dimensions, the third front is theory, quiet, relentless work. Physicists are trying to build a complete picture. One that can finally answer the stability question. That means moving beyond the standard model, which we know is incomplete. The biggest challenge is integrating quantum mechanics with gravity. A theory of quantum gravity. In that framework, the behavior of the Higgs field and the structure of space-time would be described together. The instability suggested by our current, separate models might resolve. Or it might crystallize into a firm prediction. Theorists also work on models of the early universe, like inflation, with greater sophistication, trying to understand exactly how the fields we see today were set into place. Was it random or was it inevitable? This three-pronged effort, smashing particles, surveying the sky, refining equations, it shows a species leaning in. With curiosity, with rigor, not turning away from a potentially unsettling truth, the drive to understand the ultimate fate of our cosmic home, whether it offers permanence or reveals a fragility. It's one of the most noble expressions of the human spirit. We're building better tools to listen to the universe's deepest whispers, ready to accept whatever story they tell. That knowledge can sit in the back of your mind. There's an old story, the sword of Damocles. A king had a sword hung above his throne, held by just a horsehair. He let his guest, Damocles, sit in the king's seat to feel what that power was like, but Damocles could only see the blade right above him, knowing it might fall at any second. The story is about the danger that comes with great fortune, and our situation is like that, but cosmic. We've been given this universe, this throne of stars and galaxies. It's beautiful, complex, but our physics says there might be a sword hanging over all of it, a thread of quantum chance, holding back a quiet change. For most people, the timescales are so huge, it feels abstract, theoretical. It's easy to put it aside, just an interesting scientific idea. The odds are so incredibly small. It doesn't belong in our daily thinking. We plan for tomorrow. We worry about closer things. The universe's possible instability becomes background noise. Not a real fear, but for some, the idea lands differently. It can create a kind of cosmic anxiety, a sense that the ground of existence might not be solid. That every stable moment is just a temporary pause. It's not panic, it's a deep unease, a recognition that all our work, all our history, everything we aspire to, it's all built inside a window. And that window has no guaranteed length. It can make the vastness of space feel not just awe-inspiring but fragile. This psychological effect is real. It's often unspoken. It's the shadow side of being able to understand reality's deepest rules. We can find truths that are hard to hold emotionally, but that same knowledge has a counterweight. It can be freeing. The sword is hanging by a thread, yes, but that thread has held for 13.8 billion years. The fact it holds right now, that we're even here to think about it, that's a miracle. A staggering piece of luck. Our stable cosmic epoch, this arrangement of physics that allows atoms and planets and life, It's not a given, it's a gift. An incredibly rare and precious chapter in reality's story. Knowing it could end randomly at any time, that doesn't have to make it worth less. It can make its worth stand out more sharply. Every sunrise, every connection, every act of creation or discovery, they become more meaningful because they happen inside this temporary, golden age of stability. The sword above makes the feast below more precious. How we take this in says a lot about us. Some people react with fear. They choose not to look up at the blade. Others meet it with indifference, a rational dismissal of a risk too remote to care about. But there's a third way, a path of clear-eyed appreciation. It means accepting the possibility without being frozen by it, using that awareness to engage more deeply with the present, to live with wonder, knowing the stage itself is a temporary, magnificent artifact. This is where frontier science touches something ancient in us. It asks how we find meaning and purpose not in spite of uncertainty, but within it. The universe might be on borrowed time. Our response can be to make that borrowed time matter, to fill it with the very things its fragile laws make possible: curiosity, compassion, and the relentless, beautiful pursuit of light. The universe could go through a phase transition. To get a sense of that, you can look at simpler ones, like a glass of very pure water. You can cool it way below zero, and it can stay liquid. That's supercooling. The water molecules are holding on, resisting the change to ice. The system is in a higher energy state, a liquid, when the lower energy state, a solid, is actually available. It's metastable. All it needs is a trigger, a tiny ice crystal, a speck of dust, a tap on the glass that acts as a seed, and once that seed is there, the transition is explosive. The supercooled water doesn't freeze slowly from the edges. It crystallizes almost instantly throughout the whole volume. In a flash, the liquid becomes solid. Its entire nature is reshaped. The properties that defined it, how it flows, its clarity, how it interacts with light, they get replaced by a new set of rules. That's the essence of a phase transition, and it's the closest analogy we have for vacuum decay. Our universe, with its specific laws, might be like that supercooled water, existing in a delicate, higher energy configuration, seemingly stable for eons, but not in its most fundamental, lowest energy state. It's waiting, and all it would take is a single quantum seed, a random fluctuation in just the right place, to trigger the crystallization of a new reality. Or consider another example, a bottle of soda shaken but unopened. The liquid inside is under pressure, saturated with dissolved carbon dioxide. It's in a metastable state. It can sit on a shelf for months, looking perfectly calm, but everyone knows what happens when you twist the cap. That simple action breaks the seal, releases the pressure. And the transition is rapid and total. Bubbles erupt everywhere at once. The whole system shifts from a high-pressure liquid to a lower-energy state of foam and released gas. The nature of the contents is completely transformed. You can't get the soda back. The process is irreversible. This, too, mirrors the cosmic possibility. Our vacuum might be under a kind of quantum pressure, holding its fields in a specific, tense arrangement. The formation of a true vacuum bubble would be like twisting that cosmic cap, releasing the pressure and letting the entire system rush toward its true, lower energy foundation. The transition wouldn't be a local event. It would be pervasive, rewriting the substance of space itself. These analogies aren't perfect. The universe isn't made of water or soda. The quantum fields are far more abstract, but they serve a purpose. They translate an almost unimaginable cosmic process into a human-scale experience. They help us visualize how something can appear perfectly stable for an incredibly long time, only to undergo a sudden, total transformation when the right conditions are met. The key insight is that stability isn't always permanent. Sometimes it's a temporary balance, A system can be caught in a local valley of stability, not the global one. And escaping that local valley requires just the right nudge. For the supercooled water, it's a seed crystal. For the soda, it's opening the cap. For the universe, it might be a random quantum event, a tunneling through the energy barrier that has held our physics in place since the beginning. These everyday transitions remind us that change isn't always gradual. It can be instantaneous and absolute. The universe we know could be living in such a moment, suspended in a temporary configuration. And the next phase of reality, whatever it may be, is waiting for its trigger. That finality touches something deep in physics. Information isn't supposed to disappear. In our universe, quantum mechanics says information is always preserved. It can be scrambled, it can be transformed, but it's never truly lost. You take a book and toss it in a fire. The paper burns, the ink turns to ash, but in principle, if you could track every particle of smoke, every photon of light, and reverse the process, you could reconstruct the book. The information about the words is still there, just in a vastly more disordered form. That's a bedrock principle. It's why the black hole information paradox is such a crisis. When something falls into a black hole, does the information vanish when the black hole evaporates? That would break quantum mechanics. Most physicists think the information is preserved, maybe encoded on the event horizon like a holographic imprint. But vacuum decay is different. It's not about information being hidden or scrambled. It's about the medium for information being erased. In a decay event, the complex structures that hold information cease to be possible. A star's fusion history, the genetic code in a cell, a memory in a brain, these are all specific arrangements of matter. They're patterns written in atoms, in forces, in the specific constants of our physics. And when those constants change, the language itself is lost. The new physics in the true vacuum likely wouldn't support atoms, or molecules, or any stable, complex structure. It would be like taking a novel and not just burning the paper, but changing the fundamental rules of language and alphabet so the concept of a word no longer exists. You can't reconstruct the story because the framework for storytelling is deleted. The information isn't transferred, it's rendered meaningless. The cosmic hard drive isn't just wiped, the operating system that can read any data is uninstalled. This challenges our most resilient ideas about reality. It suggests a cosmic ending so absolute that not even the ghost of what was remains, no hologram on a bubble wall. No quantum resurrection, just a silent transition to a simpler state where the past has no translation. For all we know, our universe could be the successor to a previous one that underwent such a decay. Its entire history, its civilizations, its wonders could be gone without a trace, overwritten by our own Big Bang. We would have no way of knowing. That possibility places our own story in a stark light. Every achievement, every loss, every quiet moment of beauty, it all exists within a temporary code. A code that could be replaced, leaving no record that it ever ran. This isn't pessimism, it's a reflection on existence in a quantum cosmos. Our reality might not just be finite in time, its meaning might be anchored in a physics that is itself temporary. And when that physics changes, the anchor dissolves. All the evidence points to an absolute end, a blank slate, but the human mind resists that finality. It asks, what if the true vacuum isn't just an empty void? What if it's a different kind of order? This is the most speculative edge of the idea. Could vacuum decay be beneficial from a cosmic perspective? Not for us. The wall of transition would unmake every atom in its path, but for the universe as a whole, could it be a kind of rebirth? Some models allow for a true vacuum state that's still rich with possibility. The new constants of nature might be different but not barren. They could permit stable structures under entirely alien rules. Particles we can't conceive of could form bonds in ways that make our chemistry look primitive. A form of complexity might emerge, even something like life. It would bear no resemblance to anything we know. Its logic, its substance would be foreign. This is pure conjecture. The energy released at the bubble wall as the fields snap into the lower state is unimaginable. It would likely scour away any pre-existing structure, any potential for carrying information from the old universe into the new. The transition seems to guarantee a clean break. And yet the thought experiment persists. It pushes the theory to its limit. It asks not just about an ending, but about a potential beginning. Could the silent erasure of our cosmos be the necessary labor pains for a stranger universe to be born? One that might be even more complex. In this view, vacuum decay isn't a deletion. It's a cosmic reset button. Our universe, with its delicate balance, might be just one epoch. One phase in an endless cycle of transitions. Each transition wipes the slate, not into nothingness, but into a new set of fundamental rules. From that new foundation, a different story unfolds. This connects to grander visions of a multiverse, where every possible set of physical laws is realized somewhere in some bubble. Our bubble's end might be the moment another, very different bubble begins right here. We are so attached to our particular physics, to the beauty of atoms and stars, we view their loss as the ultimate tragedy, but from a truly cosmic vantage point, one that sees beyond our local laws, it might just be change. The end of one pattern making way for the next. This speculation offers no comfort for us trapped within this pattern, but it does expand the imagination. It asks us to see the universe not as a single, linear story, not with one inevitable conclusion, but as a potential tapestry of realities, each with its own rules, its own wonders, and its own eventual transformations. The silence following a decay might not be an eternal silence. It might just be the quiet before a different kind of music begins. The story of vacuum decay is really a story about science. We want certainty. We want to know for sure, yes or no, what will happen to the universe. But science doesn't give that kind of certainty about the future. Not on this scale. It works with models. It works with probabilities, the best evidence we have right now. All of this, our whole idea of whether the vacuum is stable, it comes from the standard model of particle physics. It's an incredible model. It explains almost everything we can test, but we know it's incomplete. It doesn't have gravity. It doesn't have dark matter. There are gaps, so when we take our measurements and we put them into the standard model equations, and the answer says the vacuum might be metastable, we have to hold that answer carefully. It's the best answer we have with our current tools, but it's not the final word. It's just a snapshot. A picture of what we think right now. Future discoveries could change everything. A new particle from a new collider could add a stabilizing force we never imagined. A better theory of quantum gravity could show us the vacuum landscape is totally different. Or it could go the other way. New data could make the case for instability even stronger, make it a near certainty in our models. We're navigating with a map that's still being drawn. We see the outlines, but there are still blank spaces, whole areas we haven't charted, and that uncertainty, it's not a flaw, it's the engine, it's what makes us build bigger experiments. Look deeper into space, refine the theories, we follow the evidence even when it points to something unsettling, like a universe that might not be permanent. That's the only honest path, so vacuum decay is about more than cosmic fate. It's a lesson in the limits of what we can know. It takes courage to stare into that kind of ignorance. To ask the biggest questions anyway, knowing we might not live to see the answers. We're the kind of species that can imagine the end of everything, but we can't say for sure if that end is already written. We're suspended between what we know and what we don't, using the light of our knowledge to explore the mystery. That tension, that acceptance of not knowing, it might be the most human part of the whole story. We build our understanding piece by piece, comfortable with the idea that the final piece might always be just out of reach. This idea goes back further than science. It's really philosophy, even touches on old religious questions. The thought of a total, silent end for everything, that's not new. What's new is we might have the math for it. Philosophers have always dealt with limits with meaning. If a universe can end by accident, a random quantum event, then what does that say about purpose inside it? Some traditions see a kind of stark mirror here. It challenges the whole idea of a cosmic goal, that the universe is headed toward some intended finish. Vacuum decay says the opposite. The final end could just be an accident, a random fluctuation that forces a shift. Meaning isn't waiting in some final chapter. It has to be built, lived, held onto inside the temporary story itself. Our projects, our ethics, our search for beauty, they become these brave assertions against a cosmos that doesn't offer any final guarantee. And that dialogue goes further. In a lot of religious thought, stories of an ultimate end are central. Judgment, renewal. The imagery is dramatic, fire, flood, making way for a new world. Vacuum decay, in its sterile science language, paints a parallel picture, a complete, instant transformation of reality, wiping the old order clean for something entirely new. Theologians might see in that not proof, but a point of contact, a place where scientific description and mythological imagination circle the same deep mystery. The end of everything we know. It doesn't validate any one belief, but it shows how a modern scientific idea can suddenly light up how old and universal these questions are. We've always looked up and wondered about the end. Now we have equations for one possible version. That's where the understanding gets deeper in this conversation across fields. Physicists give the rigorous framework, the math of fields and probabilities. Philosophers work through what it means for ethics, for knowledge, for what it is to exist here. And from theological angles, people can reflect on how this science meets stories of creation and destiny. Wrestling with these links doesn't blur the evidence. It makes the conversation richer, more complete. It shows that trying to understand the cosmos isn't just about data. It's part of a much older human search. A search to grasp our place inside a reality that's awe-inspiring, beautiful, and fragile. So vacuum decay, in all its technical detail, becomes a modern container for some of our oldest wonders. It reminds us that asking how the universe works is tied up with asking what our being here might mean. Telling this story is a challenge. How do you explain a concept that could rewrite the universe using only the language we have now? For scientists and educators, communicating vacuum decay is a delicate act. You start with the familiar. You talk about fields like the Higgs field as invisible presences filling space. You explain energy states with marbles in valleys or supercooled water waiting to freeze. These are the footholds, the analogies that give our minds a place to stand. But the next step is crucial. You have to separate what we know from what we might imagine. The established science is clear. We have quantum field theory. We have the measured mass of the Higgs boson. The equations from those facts point toward a metastable vacuum. That's the solid ground. The speculation begins when we ask what happens next. Will a bubble form? What's inside it? Here, responsible communication resists the easy headline. It avoids shouting that the universe could end tomorrow, because that's not what the science says. The science speaks in probabilities so vanishingly small they defy everyday understanding. It speaks in timescales that make human history look like a single heartbeat. The goal isn't to scare but to illuminate, to take a public that may never study differential equations and give them a meaningful glimpse into one of the most profound ideas in modern cosmology. This means being honest about the uncertainties. We don't know if our vacuum is truly metastable. We don't know if new physics will change the story. We can present the possibility, explain its basis, and sit with the audience in that space of not knowing. It's a space of wonder, not panic. When done well, this communication does something powerful. It empowers, it allows people to engage with a staggering cosmic concept on their own terms. They can feel the awe of a universe balanced on a quantum knife's edge without being paralyzed by a fear they can't act upon. It fosters a shared sense of curiosity about the fragile, mysterious architecture of reality we all inhabit. In a world flooded with information, this task is more vital than ever. An informed society isn't just one that knows facts. It's one that can grapple with the implications of those facts, that can hold the idea of a temporary cosmos and still find deep meaning in a sunset, a discovery, or a connection. By explaining the inexplicable with care and nuance, we don't just share science. We invite everyone into the ongoing human conversation about our place in the story of everything. The bubble wall reaches you at light speed. There's no warning, no flash, no countdown. The signal of its arrival moves with the transformation itself. You'd have 0 seconds. Your last conscious moment would be the last moment your brain could work under the old laws. Then, in a time too short to measure a Planck instant, the rules change. The Higgs field drops, the constant shift, electromagnetism, the nuclear forces, the particles in your neurons, their masses and charges, they're redefined. And the pattern of electrical impulses that is your mind, your memory, your self, that pattern depends on those constants holding stable. When they change, the pattern dissolves. It's not erased like data on a corrupted drive. The drive itself becomes a different object, one that was never meant to hold that data. There's no pain, no fear, no time for a final thought. The machinery of experience is turned off not by damage, but by a rewrite of its operating manual. One state of being ceases. Another begins, a state incompatible with the complex existence you knew. That's the otherness of vacuum decay. It's not a disaster that happens to the universe. It's the universe undergoing a phase transition. You're not an observer watching the stage collapse. You're part of the stage, and the stage is becoming something else. In that final sliver of time, there's no room for experience, no memory, no legacy. The story isn't ended with a period. The alphabet the story is written in is replaced. A new set of symbols that can't form the old words. This thought experiment, it serves a purpose. It strips away the cinematic imagery, explosions, cosmic drama. It forces us to see vacuum decay on its own terms, a silent, instantaneous reconfiguration of reality's foundation. The experience isn't destruction. It's replacement, and in that replacement, the concept of you, a conscious entity bound by our physics, it has no translation. It highlights a boundary. We can describe the mechanism with math, but we can't truly imagine the subjective reality of its consequence. Our imagination is a product of the very physics that would be overwritten. The silence that follows isn't an empty silence. It's the silence of a different set of rules, playing a game we will never know. Even unsettling questions leave something behind. The idea of vacuum decay, as remote as it is, changed how we look at the cosmos. It pushed quantum field theory, forced physicists to refine their equations. The tools built to probe the vacuum's stability, more powerful colliders, sensitive space telescopes, they do more than test one idea. They let us test other grand theories. Map the early universe with more precision. Search for dark matter, dark energy. That's how science often goes. A single profound question, even about an end, becomes a catalyst. It drives new technology, new math, new ways of seeing. Trying to understand if our universe is permanent has, strangely, accelerated our understanding of everything in it. And it reflects something about us, asking these ultimate questions: where we came from, what our fate is, how fragile reality is. That's a human trait. We're the species that looks at the silent stars and wonders not just about their light, but about the stage they shine on. We build machines to smash particles, not for destruction, but for revelation. We send telescopes to the edge of space and time, looking for clues in ancient light. That drive to know, to comprehend our place, it persists even when the answers point to vast, impersonal forces. Or a cosmic fragility, it's curiosity that outweighs fear, a willingness to stare into the abyss not with dread, but with a need to understand what, if anything, is looking back. That legacy of inquiry might be the most enduring response to an idea like vacuum decay. The hypothesis itself may stay forever untested here, but the journey of exploring it has value. It teaches humility before the scale of reality. It sharpens our tools, and it reaffirms that our greatest asset isn't the promise of permanence, but the capacity for wonder. In a universe that may or may not be stable, our relentless curiosity becomes its own anchor, a light we carry, illuminating the mysteries for as long as our particular physics lets the light shine. We end back where we started, with empty space, with that silent energy. We've walked through quantum fields, looked at the structure of the Higgs, and considered a wall of light that could change everything. That's vacuum decay. It's a theory that shows our universe might be temporary, a kind of stable masterpiece balanced on an edge. The constants we know, the rules, they might be borrowed. They might not be permanent, and the theory shows how it could end, a random fluctuation, a bubble of new physics. It would grow at light speed. It would transform everything it touched. Erase stars, planets, all of it. The math is elegant, the mechanism is precise, but the real weight of the idea isn't the destruction. It's what it says about our existence. It asks what it means to live, to wonder, to build things, inside a window of time that isn't guaranteed. The chance of it happening here, now, is incredibly small. Unimaginably small. You'd see 1,000 other impossible things first. This isn't a prediction, it's a revelation about reality itself. Our stable time with galaxies and life might not be the default. It could be a rare chapter, a temporary set of laws that let complexity happen. Knowing that doesn't have to make things feel small, it can make them feel larger. Every sunrise, every kind act, every question we ask, they look different against this backdrop. They become affirmations, assertions, made inside a fleeting moment of possibility. So vacuum decay, in the end, isn't really about an ending. It's about a beginning. It asks us to see the universe differently, to see the staggering improbability of this stable stage we're on. Our whole history played out here. It challenges us to find purpose not in what lasts forever, but in what we do now, in this temporary stay, to engage with the mystery. To pursue understanding, to cherish the connections we make. The cosmos might be silent about its fate, but our questions are still there, echoing, a testament to the wonder it created.